Welcome back. In this video, we're now ready to look at the actual concavity and inflection points for the equation y equals x cubed minus 5x. In the last video, we actually looked at the graph of that thing and kind of discussed graphically what the concavity and points of inflection looks like. Now we're ready to see exactly when does that happen. So the key, as we saw, was concave down when the second derivative is negative, concave up when the second derivative is positive. So we begin by finding the derivative. So we differentiate very easily. Y prime is 3x squared minus 5. Y double prime would be 6x. And now we want to look for when is that derivative, 6x, positive, when is it negative. Well, remember, to solve an inequality, we figure out when that thing is 0. Y double prime equals 0. It happens when x is equal to 0. So when 6x is 0, that would be when x is 0. And also, although it's not important in this problem, when is y double prime undefined? In this case, it's never going to happen. Okay, so those are kind of the analogs to the critical values that we found with the first derivative. So once we have all those values, we then graph those on a number line, and then we're going to test some points. Now we want to know the sign of the second derivative so we can talk about concavity. So it's the second derivative that we're going to evaluate at points on the two sides of 0. So I try -1. If I plug -1 into that, I get -6. So the second derivative is negative there. And pick something bigger than 0, say 1. And if you plug in 1, you get y double prime is 6. So it's positive in that region. Okay, and once we know when the second derivative is positive or negative, we can then talk about when it's concave up. That would be when the second derivative is positive. So that would be from 0 to infinity. We could talk about when it's concave down. That would be when the second derivative is negative. So from negative infinity to 0. Okay, so that's the concavity. What about the inflection points? Well, inflection points are actual points on the graph where the concavity changes. Now we can see the concavity changes at 0 from concave down to concave up. But is 0 actually a point in the graph? So at this point, we evaluate our function at 0 to see, is it actually a point in the graph? And if so, what is the y-coordinate? Well, we plug the 0 in. We see that the y-coordinate is 0, so the point would actually, on the graph, would actually be 0, 0. So now we can say that 0, 0 is an inflection point, or a point of inflection, or as I like to abbreviate it, a POI, or in other words, a POI. So now we've found what we've been asked for. When is it concave up? When is it concave down? What are our inflection points or points of inflection? Okay, well, now I want to take a look at the graph. This is the same graph we had before. Only now I've blown it up a little bit more. And here I can see that my graph is concave down. If you want, you can say it this way. It's concave down like a frown. If that helps you remember it shape-wise. In the area that I've highlighted in red, it's concave up like a cup, where I've highlighted it in blue. And then I have this point at 0, 0, which again I refer to as a POI, my point of inflection. Okay, in the next video we're going to look at another example of finding concavity and points of inflection. Next example will be a little bit more involved, and what really happens here is the difficult steps become sometimes getting to that derivative. So till next time.